Hello, everyone. All right, this week we're going to talk about Chapter 8, and I wanted to start out by just reviewing some of the important concepts from Chapter 7. So, Chapter 7 was on work, and Chapter 8 is on energy and conservation of energy. And energy is very closely related to work. So, let's start by reviewing that. Now, first let's talk about the dot product. So a dot product is a way to multiply two vectors together to get a scalar quantity. It looks like this, A dot B, and it is equal to the product of the magnitudes of the two vectors times the cosine of the angle between them. And you can see here that, so by choosing the cosine of the angle, you see you're essentially picking out that component of the one vector, which is along the other vector, and then multiplying those two things together. So dot products get larger if the two things are pointing along the same direction, and they get smaller if the two things are at, say, right angles to one another. When they're normal to one another, then the dot product is 0. If they're pointing in opposite directions, then you get a negative dot product. And another way that you can write it is if you express the vectors in terms of their components, as I've done here, is that A dot B is the product of the x components plus the product of the y components. And if I had z components on these vectors, then there would also be plus AZ times BZ. Okay, and work is defined in terms of a dot product. When f is constant, work just is the dot product between work and displacement, as I've written here. So work is always done, the work done by a force on an object is always a force acting over a displacement. So when a force is acting on an object that doesn't move at all, then there is no work done. And similarly, when the force is perpendicular to a displacement, then again, no work would be done. So this would be the case in, say, circular motion if I'm swinging a ball around on a string, or in the case of a circular orbit, the force and the displacement are always perpendicular to one another, so the dot product between the two is 0. Now, what happens when work is or when force is not constant, when it is varying? Well, what you could do is chop up the force into little pieces, chop up the displacement into little pieces, multiply those little pieces together, including that cosine of the angle between each one of those little pieces, and then sum all of those little pieces up together. That would look something like this, and so something like this here. And what that would turn out to be then is the area underneath this f cosine theta curve, where on the x-axis we have distance here. There's another way to write this, and it is in terms of an integral, right? So work is the integral between the starting point to the final point of f dot dl, where dl is a displacement element. So this ends up being the area underneath the f cosine theta curve, where on the x-axis we have the displacement L. So if this looks scary to you, if the work expressed as with both an integral and a dot product together, I know that can be a little bit intimidating. But you can always think about it this way, right? That dl is going to be some, oh, this should have a d. There should be a dlx, a dly, and a dlz, so displacement elements along the x, y, and z axis. And then you could write it out this way, as work is the integral from ax to bx of f, the x component of the force, dlx, so the displacement element in x, and then the same thing for y and for z. right? Notice that there's no components here. This isn't like the x component of work. There is no such thing as the x component of work because work is a scalar quantity. It's just that this is the way that these dot products work, right? You could write this out in terms of the multiplication over each one of the individual components. And so you can sum them together from the different components if this looks less scary to you than this ugly thing where there's both a dot product and an integral. So another thing that we talked about in chapter 7 was kinetic energy, which is the energy of motion. Okay, so kinetic refers to motion, just like how kinematics was the topic we were studying when we were talking about objects moving. So kinetic energy is the energy due to motion, and it's equal to 1/2 mv squared. And then we also talked about the work energy principle, which is a very useful principle. It's very helpful for solving problems. The work energy principle says that the net work done on an object, equals the change in its kinetic energy. So the final kinetic energy minus the initial kinetic energy is equal to the net work done by all forces acting on an object. Let's do an example from chapter 7, and we'll use this to introduce some of the concepts from chapter 8. So here, this is example 7.2 from your textbook. You're asked to determine the work a hiker must do on a 15-kilogram backpack to carry it up a hill of height h equals 10 meters. And then you're also asked to find the work done by gravity on the backpack and then the net work. So the first step to this problem would be to draw a free body diagram, and that's already done for us here. And then to pick out a coordinate system, and that's already done for us there. And next would be to say sum up the net forces, and then break these into components and solve the equations for whatever you're asked to find. And then to find the work would be the last step by taking the dot product between each of the forces and the displacement vectors, and then sum them up to get the total work, or the net work. So the net force on the object, right, is going to come from these two forces, the force of gravity pulling it down and the force of the hiker pushing it up on the backpack. We're told to assume that the motion is smooth and at constant velocity. So in other words, the acceleration is 0, which means that, right, the net force is going to be equal to 0. And so these two forces here, the force of gravity and the force of the hiker, are going to be pointing in opposite directions, and they will have the same magnitude. So the force of gravity is, of course, pointing down here, and the force that the hiker exerts is pointing up, and the force that the hiker exerts in order to maintain this at least an average, the acceleration is 0, which must mean that the force that the hiker exerts exactly balances that from gravity. So the force the hiker is equal in magnitude, and it is just opposite in direction. So it has a plus sign here instead of that minus sign there. Then the displacement vector is going up a distance h, which is the one that is interesting to us, and then it has also got this x component, which we don't know this distance here. We're not told that in the statement of the problem, but that's okay because we'll see how that doesn't matter. Now, in part A, then I'm asked to find the work that the hiker does, so that would be this part here. Work is, in this case, where we have constant forces, force dot displacement, and you'll see that the force only has a j hat component, so it only has a y component, and so this x unknown here won't come into play at all. I take the dot product between these two, I get a mg, a plus mg, times h. Multiplying together the two y components, and the x component of the force is 0, so that part goes away when I take the dot product. So I could plug in numbers, and if I did that and I plugged in the 15 kilogram mass times g, which is 9.8 meters per second squared, times h, which is 10 meters, I would get that this is plus 1470 Newton times meters. This would be my answer to part A. And then my answer to part B would be, so in part B, I'm asked to find the work done by the force of gravity. So if I take force of gravity dot with the displacement vector, of course, I'm only going to get, the only difference is going to be that I will pick up a minus sign because the force of gravity is just going in the minus y hat direction. So this, of course, then will give me a work that is minus 1470 newtons times meters. Then in part C, I'm asked to find the net work done on the backpack. And so in part C, then, I would have, well, the net work done is going to be equal to the work done by each of the individual forces. And of course, they are opposite in sign. So I end up with this being 0 times meters. And this makes perfect sense, right? That the net force would be 0 because of what you know about the work kinetic energy theorem, and because you know that this happens at constant velocity, right? So if it happens at constant velocity, then the initial and final velocities are going to be the same. So the net work, which is equal to the change in kinetic energy, has to be equal to 0 because the kinetic energy will not change at all if this happens at a constant velocity. So now that we've done this, let's just talk about this factor here, this mgh that shows up here, this minus mgh that shows up here, and let's relate this to chapter 8. Now, you might remember from Dr. Olson's lectures on chapter 7, he did an example where a ball was thrown up in the air and one where one was dropped from a height h, and this factor here of mgh showed up in that exact same problem. And there is another way of thinking about this mgh. Instead of thinking about it in terms of the work done by specific forces, you can think of it in terms of potential energy. PE is short for potential energy, specifically gravitational potential energy. So in chapter 8, we'll be talking about mechanical energy. And mechanical energy comes in two forms. There is kinetic energy, which is the energy due to motion, and there is potential energy, which is the energy due to an object's position or configuration. And these two together make up a total mechanical energy for a given system. And mechanical energy is always conserved. The definition of mechanical energy is the ability to do work. The fact that the ball, when it is up here, a height, say a height h above the ground, means that it has the potential to do work if you let go of it. And after it is thrown up from the ground, it is moving with some speed, some kinetic energy, and that kinetic energy that it possesses at that point gives it the ability to do some work. So both of these are included in the definition of mechanical energy. And mechanical energy is conserved, which means that so long as I am working with a well-behaved force, and I will define exactly what I mean by a well-behaved force later, the initial mechanical energy of a system is equal to the final kinetic energy of a system. So there is no change in the mechanical energy of a system so long as the forces that are acting on it are well-behaved, or the better word for well-behaved is conservative forces. Conservative forces are those forces which conserve the total mechanical energy of a system. Now, the way that you calculate potential energy is to calculate the amount of work that an external force would have to do on a system in order to bring it from one location to another. So you know the definition of work. It's the integral of force, so in this case some external force, dot dl, where dl is some displacement. And you might remember that for integrals, we're either going to have a definite starting location and final location, in which case we'll go from B to A, or you might have an indefinite integral, in which case there is some arbitrary constant that is going to be thrown in here. And since potential energy, which we sometimes also give the symbol U for, U or just PE, we are always going to be talking about a potential energy with reference to some starting and final point. Potential energy doesn't have some overall absolute value independent of which coordinate system you pick. Rather, the change in potential energy between 2 points is what we're more interested in. That does have a well-defined value. The change in potential energy is equal to the work that an external force would have to do in order to bring an object from, say, point B to point A. Now let's relate this to the gravitational force. Here, we have an object that is moving up an inclined plane. So the object, as it moves up, ends up gaining potential energy. How do I know this? I know this because if I take the work that an external force would have to do, in this case, the external force is the force that the hiker exerts in carrying the backpack up the hill, I will find that the force that the hiker does brings about some positive amount of work, right, as we found right here in part A. And the amount of work that is done by this external force is equal to m times g times the height h. This is exactly the definition of potential energy, a height h above wherever you set your reference point. So in this particular problem, there was a very convenient reference point, right? We could set this to be where y equals 0, and then this location up here would be where y equals h, right? Notice that I could change this around. I could make, say, I'll use a different color just to show that this would be a different coordinate system, right? I could have chosen, say, the top to be y equals 0, and then the bottom would have been y equals minus h, and that would have been fine as well. The overall change in potential energy would be exactly the same. It's independent of your coordinate system, right? So nature is always indifferent about which coordinate system you use, so long as you apply that coordinate system consistently to all parts of the problem. So let me just say that one more time because it's an important point and I want to make sure it's perfectly clear, right? The change in potential energy between this location here and that location here, the starting and final location, is well defined. It is exactly mgh. If you want to talk about the potential energy that the backpack has at some location, the value here and the value there, those values will depend on your coordinate system, and they are not well defined. The difference between these two, the potential energy here and the potential energy there, that is well defined. Okay, now let's make sure that we're being technically precise about this. So this is the gravitational potential energy of the mass Earth system. To say that it is the gravitational potential energy of the backpack of mass m is not quite precisely right. The right way to think about it is that is the gravitational potential energy of the mass Earth system. So the two objects in combination technically possesses the potential energy. So then the gravitational potential energy of some mass m near the Earth is defined in this way, and the change in potential energy between 2 points is going to be m times g times that change in y between the final point and the initial point, y final minus y initial. Now this is the formula for gravitational potential energy. Potential energy does not have a single nice looking formula like this that is the case with kinetic energy, right? Kinetic energy, you can always write that kinetic energy is 1/2 mv squared. potential energy is going to take a different form depending on what kind of force you're talking about. In general, it is always the case that you can say the change in potential energy, sometimes we use PE, sometimes we use U, is equal to the work that an external force would have to do in order to bring something from the initial location to its final location. Sorry if the B and A up here were confusing you. Just think about it this way. The integral is always from the initial location to the final location. So I like putting it this way. You'll sometimes see it written as it is the negative work of the internal forces. And that is also true. What I like about writing it this way, the external work, is that, so just looking at this, this case here, right? There is an external force that brings about this rise in potential energy. And I like this way of writing it because it tracks with your intuition. Your intuition is, if I introduce a force into this system and I externally bring in a force that raises up this backpack, raises its location, then I am adding some potential energy to the system. And that should make sense. Although mathematically speaking, you could also write this is equal to negative the work done by the internal forces to the system, or minus the work done by the force of gravity. And that is also correct. All right, let's talk about why this is actually useful and helpful. Here's why it's useful. Let's say that you walk up this slope here, and then you set the backpack down because you're tired, and it slides down the ramp. Okay, and let's just pretend, for the purposes of this illustration, that the ramp was frictionless as it was sliding down, so that the only force doing any work is just simply the gravitational force, which is a conservative force. The reason why I have to pretend that there's no friction in this case is because friction is not a conservative force. So let's just say that that happens, right? This backpack of mass m slides down. Because I know that only conservative forces are acting on the system, I also know that the initial and final mechanical energy will be the same because mechanical energy is going to be conserved. And what that means is I can find the velocity of the object at every point as it's falling down by just noting that I know that the kinetic energy and the potential energy at any given location throughout the fall is going to be equal to some constant value. Right? This will not change. This is going to be equal at every value of y as the thing is falling. And this would be really helpful if I was, say, interested in the speed that this object will have as it's falling down. How does it pick up speed? Well, in the initial location, it had a potential energy of mg times h, and at a location y, at every location y along the way, it's going to have a total mechanical energy that will be equal to the potential energy at y plus the kinetic energy at that exact same time. So that's going to be equal to m times g times y, assuming taking y equals 0 at that location, plus 1/2 times m times v squared. Now, these two things are always going to be equal. So if you want to know the speed at any given point, you can write that mgh is equal to mgy plus 1/2 mv squared. And that means if I want to say find the velocity at any given point y, I can take mgh minus y is equal to 1/2 mv squared. Multiply, say, by 2 over m on both sides. That would get rid of this here, and it would give me a 2 over m on this side, so those two things would cancel out. Take the square root of both sides, and I would have that y is equal to the square root of 2g times h minus y. So what would be the final speed here? The final speed would just be root 2gh. So I have the velocity at every location y as this thing falls down the ramp. And note that I didn't have to set up an F net equals ma equation in order to do that. I could just use the conservation of mechanical energy to come up with this answer. So this is why the conservation of energy is going to be helpful for you in solving problems. Let's talk about one final thing before I move on. We'll talk about units and the experiment that brought about this unit being named after this guy. So the units of work is newtons times meters. The SI unit of work or energy is a newton meter, otherwise known as a joule. J is for joule. So it's a kilogram meter squared per second squared. So you can write newton times meter down if you want to give me units for work, or you can write joule down. They're exactly the same thing. Both of them are equal to a kilogram meter squared per second squared. So let's talk about joule and why the unit of energy is named after him. So Joule did this very fascinating experiment where he took a sealed off container filled with water, and he put a small fan inside of it that was hooked up to a crank that was extended outside of the sealed off container. And what he found was that he could introduce energy into this water here. He could introduce mechanical energy by turning this crank and introducing some swirling of the motion of the fluid inside of the container. And what he found was that exact amount of mechanical energy that he introduced into the system would, once all of the water molecules settle down, turn into that exact same amount of thermal energy inside of the water. So the mechanical energy that he introduced was conserved in the form of thermal energy, otherwise known as heat, here inside of the fluid. So even in this case, energy is conserved. So in this particular case, we're talking about two different kinds, right? There's mechanical energy up here. There is thermal energy that is produced down in the water. So this is a very broad phenomena, that energy is conserved. It happens with electromagnetic energy, it happens with mechanical energy, it happens with thermal energy, radiative energy. This is always the case that energy initial is equal to energy final. So this goes beyond just the conservation of mechanical energy. And it is one of the central, most important laws by which the universe operates. And you will learn more about thermal energy and about electromagnetic energy in your subsequent physics classes. But we're just going to focus on mechanical energy in Physics 1.